What's going on, everybody? It's Mr. Gustin back in the physics classroom. Today we're talking about all things kinematics graphs. All right, so I've got a former analysis from one of our labs. We're going to kind of talk through that, talk through some of the kinematic graphs for that lab, and then take notes specifically and review how kinematic graphs can be, or we can translate between kinematic graphs, position time, velocity time, and acceleration time. Okay, so let's come here first. We had an object that was on the ramp. It was on wheels. It was a cart, a little matchbox car. It went down the ramp, started at rest, so we can say its initial velocity was 0 meters per second, and then eventually it went down the ramp this way and back up the ramp. We can talk about the forces on there, but we're not too concerned with those right now. What we're first concerned with is the motion of the car as it moves. So we're going to track how it moves from A to B, from B to C, and from C to B, and then back from B to A. So from A to B, it looks like this object is going to move down the ramp, but speed up. And we know it speeds up because it's operating or moving in the same direction as gravity. When motion and net force are in the same direction, things speed up. From B to C now, as it moves back up the ramp, it's still moving up the ramp or along. It's moving up the ramp now, but now it's slowing down. And the reason I know it's slowing down is because as the car goes up the ramp, now it's going against that gravitational force wanting to pull it down. So I'm going to see the cart slow down. At point C, it's actually going to hit the brakes and slide back down the ramp or roll back down the ramp. So from C to B, now it's going to move backwards and speed back up. And the reason it's speeding up is because now as it slides back down the ramp, it's moving in the same direction as that net force, so we see it speed up. When velocity and acceleration point the same direction, we see speeding up. And then from B to A, it's still going to move backwards. But as it moves up the ramp, we notice that now it's moving against that gravitational force, so it's going to slow down from B to A. Now, we don't need to know a whole lot of physics to be able to consider what this car is doing, but if we do know things about physics, forces, accelerations, and velocities, we can explain them using our more physics-y vocabulary. But this is what's happening, all right? And because I discussed the motion of this car in terms of velocity, I'm going to sketch the velocity and time graph first. I think that's just easiest when I have it explained that way. So let's start. If I look at my picture, I know that the initial velocity is 0. It starts from rest as I drop it. As time goes on from A to B, it's moving forward. It's moving in the positive direction and speeding up. So I would see a constant increase in speed. It moves forward and it speeds up. From B to C, it's still moving forward. Velocity is still positive, but now it's slowing down, which means it's getting closer and closer to 0 until it reaches point C, when it does in fact stop to change directions. So I see it slowing down, getting closer to 0, because slowing down means velocity is 0. Slowing down doesn't indicate direction of velocity. It just indicates that velocities are getting closer to 0. From C to B, now it's moving backwards, which means I'm going to have to graph in my negative, or the opposite portion of my VT graph, because the velocity has changed directions. But it's moving backwards and speeding up. So I'm going to get a more negative numbers, away from 0. Speeding up means the number, the magnitude is increasing. In which direction? Backwards, negative, a bigger negative number. Finally, from B to A, it's still moving backwards, so I'm still going to stay down here, but it's slowing down, and slowing down means it's approaching 0. So there we go. I have a wonderful VT graph here. I then personally prefer, after I've graphed VT, to translate to my acceleration and time graph, because I find it really easy to read the slope of a VT graph to generate an acceleration and time graph. Because we know that in order to get from a VT to an AT, literally the slope of the VT graph is acceleration. That's the definition of acceleration, a change in velocity over a change in time. So if I look here, initially the slope of my VT graph, which is acceleration, is positive. So I'm going to graph a constant and positive acceleration. Constant and positive. Over the B to C interval, I see that the slope of the VT graph is negative. And again, slope is acceleration. So I'm going to sketch a negative acceleration. It's constant because my slope is constant. Over C to B, I see the same constant negative slope. I'm just going to continue that same constant negative acceleration. Finally, from B to A, I see a positive slope on the VT graph, and slope of the VT graph is acceleration. So I'm going to go ahead and sketch a positive constant acceleration here. What I find really interesting is that when the acceleration is positive and the velocity is positive, the velocity I see speeding up. When the velocity is positive, even though the slope is negative, but the velocity is positive and the acceleration is negative, I get slowing down. This is a way I can analyze my graph with and translate into words, say maybe for an explanation as opposed to a graphical problem. The trickier one that I think exists, and maybe it's not so tricky with enough practice, the trickier one though that I think is a little more challenging are the position and time graphs. And the reason why is because I know that the slope of a position time graph is velocity. I know this, but I have a hard time kind of turning my brain around backwards, okay? So velocity is the slope. I'm actually going to kind of maybe write this backwards also. That velocity is the slope of position and time. So it's the same statement, I just kind of flipped it around. Watch. My initial velocity is 0. Velocity is 0 to begin with. Velocity is the slope of position in time. Well, that means that my initial slope must be 0. And I'm going to start us at a position of 0 meters just because I think it's easiest given the way that this graph is drawn and where I start. So we'll call this position 0 meters over here, okay? So back to this, velocity is 0, velocity is the slope. So initially my slope is going to be 0. So I make a little teeny tiny section of slope that's very 0. At the edge of this interval, at point B, my velocity is very positive, and velocity is the slope. So I want my slope to go from 0 to pretty darn positive. So I make a little section of slope that is very positive, and I connect the slopes, 0 to positive. This right here is a quadratic function, which I would expect to see for a position time graph for an accelerating object that starts with a slope of 0 and has an increasing positive slope. That's the first section. The next section, I see my velocity gets back to 0. Velocity is the slope of the position and time graph. So I'm pretty positive here, but at the edge, I want to make sure I get back to my slope where it's negative. My slope is 0. So I'm going to connect the slopes this way. So now I see this kind of smooth increasing slope, and then a decreasing slope until I hit 0. Let's go to the fourth point in the third interval. My slope, my velocity, gets very, very, very negative, and velocity is the slope of the xt graph. So I've turned around, I'm now moving in the backward direction, which means my graph should head back towards that initial position. So I'm going to put my slope somewhere down here. And again, the velocity is very negative, so I'm going to make a teeny tiny section of slope that's very negative. There's my quadratic function that I would expect to see, and it's concave down. It's opening downward because my velocity goes from 0 to very negative, so the slope of this graph goes from 0 to very negative. Finally, that last section, my velocity was very negative, and it's approaching 0. Velocity is the slope. very negative to 0, I see this slope is going to be here. So if I smooth this thing out, this is a wonderful position and time graph for the 4 different intervals over which this car goes from A to B to C, back to B, and back to A. This was one of our labs, and it's a challenging series of graphs, but if I break it down and I understand the connections between slope and the graphs, it becomes clearer and maybe a little bit easier to chunk this problem out. Now, after we did this lab, we also took some notes. We took some notes on various parts of graphs, and the various parts of graphs and what they tell us. So what I have here is a position in time, a velocity in time, and an acceleration in time graph for an object that is simply rolling down an incline. Just an incline, and there's an object rolling or sliding down it. Its initial velocity is 0, and its initial position is 0. Okay? Initial position is 0, initial velocity is 0. And we built kind of a data table in class around this. We built a data table. I can bring you all closer just to make sure you can see all these words that are written. But our data table basically outlines the information we can gather from these graphs. And so what we see is this position in time, velocity in time, and acceleration in time graph give us a lot of information. I can analyze y-intercepts, x-intercepts, slopes, and areas of functions in order to determine things. So I'll give you a minute. You can go ahead and pause the video here, copy this in your notes. We already have discussed this. I'm just not certain that it's in your notes. So get this in your notes, pause it if you need to, because I'm going to briefly talk about some connections we see here. We've already discussed y-intercepts, x-intercepts, and slopes in previous graphs. We can talk about how the slope of an xt graph gets us velocity. We can talk about how the slope of a velocity in time graph gets us acceleration. But we haven't so much talked about how area of functions can help us. Okay? In one of our labs, we discussed how the area bound by the VT graph, the literal function, and the x-axis or time axis, this area here is, well, it's meters per second times seconds. It gives us meters. It is actually telling us what the displacement of an object is. I can use the area of this graph, bound by the function and the time axis, to tell me the displacement. It actually will help me to learn more about this graph. So the area of the VT graph informs me about displacement. Not initial position, not location. It doesn't tell me specifics. It simply tells me how much displacement I have, or the object has. What is its change in position, not exact locations. So this is an interesting tool we can use. We haven't done this, but kind of extrapolating a little bit, extending our thinking a little bit, I wonder what may happen if I take the area bound by the AT function, the time axis. This is a rectangle in this graph, but I wonder what this area might tell me. So I'll take my units for acceleration, meters per second squared. I'll multiply it by the time axis, which is seconds, because the area of this would be A times T. And when I do that, what I find is that my area will have units of meters per second, which is crazy. Meters per second is a measurement of velocity. So the area of my AT graph actually informs me about the change in velocity that an object is undergoing given a certain AT graph. So thinking back this way, the AT graph's area informs me about velocity. Not a specific velocity, not a final velocity. It informs me about a change in velocity. Okay? These are all the notes for graphing that we have so far. Make sure you have them in your notes. If you've got questions, ask. Until then, see ya!